Good morning, everybody. Welcome to class this morning. I hope you all had a wonderful, restful Labor Day weekend holiday there, um, and that you're ready and raring and willing to get back to work this week. Good morning to you, too. Casey. Thank you. So we're starting module 1 this week. We're actually getting into some of the content. And what I like to do in this class especially is I like to start off by just having a look at some of the history of things that kind of surround the stuff that we'll be doing for the remainder of the semester. So my first module is always about the history of this kind of stuff. For the interest of time, just to keep our live stream relatively short, I'm going to leave out the history of computers. I got a nice video in the module for you on that. But I'm going to try to talk about both the history of programming and the history of the internet for you all today, time permitting. Again, videos are also in the modules. I might just hit some different topics a little bit differently in the live stream. But again, like the big thing here is that we're approaching this big subject of web, of programming, of databases. And in order for us to understand kind of where we are or where we're going, I feel that it's important for us to kind of understand how we got here. And one of the things that, we often say when we're examining kind of the past is we say that we're standing on the shoulders of giants, the accomplishments and the thoughts and the work put in by people who came before us are really, that's what allows us to do what we do today. So I do think it's important to have a look at this stuff to kind of provide context for everything, if you will. So we're going to be looking at the history of programming, especially today. Also, time permitting, we'll be looking at the history of the internet. And again, we'll kind of be skipping our little history of computers talk for now. But you can watch the little video that's in the course for a rundown on that. So when we're looking at the history of programming, we kind of have to understand how programming began and kind of where it's going. And that's what our presentation here kind of looks at. So we start at a time of pre-programming, and we'll be moving kind of into a modern time with the idea of machine learning and everything that's kind of in between there. So let's start out by having a look at pre-programming. And the earliest programming, or the earliest pre-programming that we can see actually started in 1801. Right, 220 years ago, we got these things that would become kind of the foundation for what would be modern programming. Joseph Marie Jacquard, like you might have heard of Jacquard fabric, this is Jacquard, this weave is a Jacquard weave or whatever. Jacquard, very big in the textile industry. And in 1801, he invented the Jacquard loom. And this loom was really one of the first of its kind. It used punch cards to control the loom. And so when we look at a punch card, and I've got a picture of a punch card here to show you in just a second. In fact, let's go ahead and pull that up here. Or, no, that must be in a different presentation where I have the picture of the punch card. Sorry. So let me just find a picture of a punch card and bring it up while I talk about this. Just so you have an idea of what we're talking about when we're making this reference. Here we go. This is a punch card. This is the kind of thing that they were writing. Were essentially the the precursors to the modern programs on way back in the early 1800s. And it was something similar to this, not this exact thing, that Jacquard was using in his loom. And so the idea here is that you see that we have certain holes punched in certain spots, and this would allow things to either get through or not. You know, when we're talking about mechanical objects, we're typically talking about, you know, pins and gears and things being allowed to make contact versus things being not allowed to make contact. And that's what we have here. So kind of the big thing to point out here, and some of the big things that we want to know about a punch card is, one, this is paper. You know, it's heavy paper. It's thick paper. Right? You know, think cardstock. But maybe a little bit thicker. Which means that, you know, once you punch a hole out of this card, it's kind of hard to unpunch it. I mean, eventually they would have means to kind of tape it up and solve things that way, but especially in the early days, if you made a mistake, you were probably starting over. Right? Because this is a piece of paper, and you can't undo that. You know, there's no Control-Z on paper, no matter how much we want there to be. Two is the way that we're kind of encoding things here, and really the way that we're kind of encoding things here is very similar to the way things are encoded to this very day when it comes to computers. You can see that we have, in this case, 10 digits, right, 0 through 9. And in this set of 10 digits, 0 through 9, you have punches. So we have 80 rows here, essentially. You can see those little numbers that are along there. You know, if we can kind of draw it in here, and we can point out our little numbers, and those are kind of our rows. And then in each of these rows, we have those 10 digits, 0 through 9, and each of these digits are either punched out or they're there. Right, and so this is how we use these things to encode data. And so Jacquard was using these to kind of encode patterns. Right, you know, if you want a particular pattern to be weaved into fabric, you could write this card and it would allow you to encode the pattern onto the card. And then Charles Babbage got the idea for the analytical engine that he could similarly use these punch cards to encode data so that the analytical engine could read information off of these cards. And we're talking about 50 years apart there. In the mid-1800s is when Charles Babbage was working on his stuff. And just for a little bit of background, I go into it in the history of computers, but since we're not doing that here, essentially the first mechanical computer was something that was ideated by Charles Babbage back in like the 1840s. Right, and it was the difference engine. And the difference engine didn't use punch cards. It was mechanically hard encoded. Right, meaning that it essentially had one function, and that was the only thing it could do. Right, with the analytical engine, the idea was we could take these punch cards and we could use it to change the function of our computer. But both of these things, the difference engine and the analytical engine, were essentially just glorified calculators, right? Like, I contend to this very day that one of the reasons why computers and programming and technology has advanced in the way that it has is because math is difficult, right? And people hate math. So when I think about like where all this came from, what we're doing with programming and the analytical engine, you know, and even today, it's because math is hard. But he got this idea to expand upon the difference engine for the analytical engine, and he wanted to be able to use these punch cards to change the functions that the analytical engine could do. Now, it's kind of important to note that the analytical engine never really took off. It was mostly conceptual, like you had like one mostly working prototype. But it was never really a thing. Like we would wait another, 15, 20 years before we got good mechanical computers like that. To put that in perspective, though, that's like right after the Civil War, yes? Like we're talking like 1870s, 1880s. So when we kind of put that in our view of history, with the first mechanical computer being at that point, and not only that, like them being programmable through things like punch cards, we can start to see the foundation of where modern programming came from. And we can see it even more when we look at this idea of punch cards in a little more depth. Let's check that out. Because really what we see when we're looking at punch cards is that we're looking at binary. And that punch card is a flexible write-once medium, right? We can only punch out the holes one time on a piece of paper to encode data that most commonly encodes 80 characters, right? Like we looked at that. That's the little row of the little numbers there. See, it goes from 1 to 80. So we're able to encode 80 characters worth of data here. Now, 80 characters worth of data, not a whole lot. And so what we would often do is we'd take multiple of these cards. Now, what's the problem with having to use multiple of these? Well, I mean, it's a stack of cards, right? Like, think about if you've ever had a stack of playing cards or a stack of papers on a table or on your desk or wherever, and then you open the window and a strong gust of wind comes through, or you turn on a fan, and all of a sudden those things are scattered. Or somebody's just a little bit clumsy and they just knock into a table and, they're scattered. What order did these go in? Did you number them? I hope so. Right, because we're talking about encoding 80 characters onto a single card. And we're talking about these being used for 60 plus years to help write programs. So they needed way more than 80 characters. I mean, even early programming languages like Fortran and COBOL were written to punch cards. So you'd need way more than 80 characters to write a program. So you'd have stacks on stacks of these cards. Right, and what's incredible is our computer still works the same way to this very day. Because of the way that our computer understands characters and letters. And we'll talk about this just a little bit more a little later on when we get into like Module 3, that sort of thing. But I want to introduce you to something else here. That really kind of sets up the fact that our computer still looks at things in this sort of way. Right? Because we say that punch cards here are essentially binary. Right? We have this row of numbers, and whether it's punched out or not, that's what's allowing us to encode a character onto this card. And so when our computer sees a letter or a number that you've typed in, it doesn't see an A or an uppercase A or a T or even like a parenthesis or whatever. It sees a number, right? And so if we look at that, that's based on something called an ASCII chart. And so let's zoom in on this a little bit so you can see it a little bit better. That's based on something called an ASCII chart. ASCII. And you can see here that we have decimal code, hexadecimal code, and octal codes for each of our standard characters. That's what's in red here. A, B, C, D, E, F, G. And so one of the things that we can look at, right, is we can look at the fact that our computer uses this binary to take these codes and encode these characters, right? So like in our punch card there, we saw that it was 10 digits, right? Like if we switch back over there really quickly, we see it's 0 through 9, and that's 10 digits. And that's 10 digits of essentially binary. But our computer looks at it slightly different. Our computer looks at it in 8 digits or octets. So there are 8 digits of binary that encode one of these characters. And so we do that by either putting a 1 or a 0 in each of these 8 digits to create that character. So let's take, for example, the lowercase letter a. That utilizes 8 bits to encode that lowercase letter a. Right? Like if we look at like data storage, advanced computer science stuff, a bit is the smallest piece of data that can exist. It's our binary unit. It's either a 0 or a 1. There are 8 bits in a byte, and so it takes 1 byte to encode 1 character. And so we use 8 of these bits, which is similar to 8 of those, which is similar to like the 10 of those spaces on that single row on that punch card to do this. So this kind of gets us back to that same way that it's there now, you know. So we're shooting for this decimal number here, which is 97. I circled the wrong one there. It's 97 for a lowercase letter a, which, as you can see, which is why we're going to talk about this even more later, that's a lot different from an uppercase letter a. That's why our computer sees lowercase and uppercase as 2 different things. But that's something else for another day. So we need to be able to encode that number 97 into these 8 bits in order for our computer to understand that that's a letter A. Right? So that's crucial here. And so that's just like punching the holes on the punch card, putting these bits in the right place. And so we do that by simple arithmetic. Like each of these locations in our octet here is its own place. Now, it's a little more complicated to think about in terms of places in our octet than it is in terms of like decimal places. Because you're used to seeing like a number like let's use the same amount of digits but put it into an put it in decimal here. So if this is a decimal number, that is 10 million. Right? And so if we look at these different places for these different values, that's 1, that's our tens place, that's our hundreds place, thousands place, 10,000s place, so on and so forth, right? Like that's something that you did like really early on in grade school math, is understanding the places for all these values. And all of the values in our octet of binary here have the same sort of place values, although they're a lot different. This is where I tell people that playing Minecraft can actually help you out when it comes to encoding and de-encoding binary. If you're a Minecraft player, these numbers should look familiar to you. This first one is our ones place. Then we have a 2's place, a 4's place, an 8's place, a 16's place, a 32's place, a 64's place, and a 128's place. So if you're a Minecraft player, you know, you see that in terms of like stacks. 64 is a stack, 32 is a half stack, 16 is a quarter stack or a stack of ender pearls, you know, that sort of thing. And it's because that all the memory and all the encoding and all that kind of stuff is based on this binary placeholder system. So that's why everything stacks up like that if you're a Minecraft player. Real easy for memory management. So now let's try to take this 97 and encode it into one of these octets. And so we do that by building our number from left to right. So we start with that number in that 128th place. And we say, okay, if I take 97 and subtract it by 128, is it a positive number? If yes, then there's a bit in there. If no, there isn't. So 97 minus 128 is negative. So that means that that is a 0. Now 97 minus 64, that's a thing. 97 minus 64 gives us 33. Right? So 64 goes all the way into 97. I put a 1 in there. And now I have 33 left over. So next I go to 32. 32 does. So I put a 1 here. That leaves me with 1. 1 minus 16, 1 minus 8, 1 minus 4, 1 minus 2. Right? Those are all no-goes there because it doesn't leave you with... So that's 16, that's 8, that's 4, and that's 2. And then 1 minus 1 is 0. So we get a bit there. So if we were encoding our lowercase letter a in binary, that's the number that we'd get, 0, 1, 1, 0, 0, 0, 0, 1. And we relate this to that punch card. We could say this in the same way. And again, if you don't quite understand the conversion process right now, that's fine. Right? We will be talking about this a little bit more later on. Right? The big thing that I want you to kind of get out of this is how we still relate this to our punch card that we were using 200 years ago. Right? Because this would be no punch, 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 no punch, no punch, no punch, no punch, punch, to encode that character. You know, we still have that similar sort of thing. And it's something that's persisted in coding for 200 years, right? So that is significant. So we see these punch cards. These punch cards have a huge impact. And the first programmer was an individual that used these punch cards to write a program. And ladies, this one's for you. Right? The first programmer is a woman by the name of Ada Lovelace. She's considered to be the first computer programmer. So the first computer programmer, by the way, was a woman. And she wrote an algorithm for Babbage's analytical engine. And it was cited as the very first computer program ever. So she was sitting there and she was punching all these holes out. And remember what the key thing was, and we'll look at this in just, it's part of the fun fact as well. But remember what the key thing was about this is that Babbage's analytical engine was never finished. So not only was she writing this program, she was writing this program without the ability to test it, which makes her even smarter. Right? And to top that all off, to go even bigger here, she theorized that the computer could one day be able to play music and chess. Put that in perspective, right? Like, we're talking about mechanical computers here. Mechanical computers. We're talking about something that looked like this. This here was sort of a recreation that was built out of the notes left for Babbage's analytical engine. This is the computer that they were using. And Ada Lovelace, even at this time, even in the mid-1800s, was like, I think computers will be able to one day play music and be able to play chess. What are the two biggest uses of computing devices today. Listening to music and playing games. Way ahead of her time. Right? This was an individual way ahead of her time, way back in, the 1850s, 1860s. Writing these programs for a computer that didn't really fully work. Postulating that one day computers would be able to play music and chess, play music and games on a computer that looked like, when their only conception of a computer is something that looked like what you see on the screen right now. If that's not incredible, I don't know what is. Like, that's someone who was incredibly smart, an incredibly smart individual. Forward thinking. Innovative. We could use a lot of big superlatives for this individual. And as we said there, this program, it was an algorithm for something called Bernoulli numbers. That's not really important. Like, we could talk about Bernoulli numbers, but it's not a big deal here. But the bigger thing is that since the analytical engine was never really finished, her program could never be properly tested. And especially once we start programming a little bit later on, one of the big things that you'll realize is the need for being able to test a program. Especially when you're doing, especially in this kind of thing. Like, you write all these programs by punching holes in cards. This write once medium. And then if you realize, like, oh, I made this little error here and this on this card at this point, I just lost a month of work. Cool. So this is a big deal. Now, we do kind of skip a lot here. I just kind of hit the high notes. Right? Like, one of the individuals that I really like to talk about in other instances is like Alan Turing. I don't mention Alan Turing here. Although I might mention, we'll talk a little bit about Alan Turing when we get to machine learning. He's one of the big influential figures that I really like as well. But we have Hermann Hollerith here. Hermann Hollerith is the next thing that I have on my list here. Because it was really the next big iteration in programming was when we saw Hermann Hollerith at his company develop the plug board. And so at this point, we're getting into kind of the electromechanical age, right? We're starting to introduce electricity into our computers. And we wanted something that was not a write-once medium that we could use to kind of reconfigure our computer, allow our computer to perform different tasks without being totally reconstructed. And that thing was the plug board. Because, you can essentially think about this plug board in the same way as, like, if you've ever seen, like, an old movie or a television show where whenever they'd make a phone call, it would immediately go through to the switchboard operator, and they'd take a plug out of one port and put it into another one. Now, again, the same basic principle of binary here applies. Right? We're still talking binary. Because either the plug board is connected and you're able to make that patch through to transfer electricity from one point to another, or it's not. So at its core, we're still using that same kind of data encoding. Plug in, on, plug out, off. And it was this computer that would lay the foundation for computers that would be a big deal 40 years later, right? Like, we had things like the ENIAC and the UNIVAC that would crack the codes to help us win World War II or whatever kind of patriotic nonsense you want to talk about there. it was this sort of plugboard technology that shaped the direction for what we would see for the 20th century computing, right? And it started right there at the beginning of the 20th century in 1906. And something that you might not know there is that Herman Hollerith was the founder of a company called the Tabulating Machine Company. That company was founded in 1896. It would 10 years later make that plugboard computer. But you might use a machine that either came from this direct lineage or a machine that has parts that came from this lineage of a company, because the Tabulating Machine Company would later become International Business Machines, which used the initialism IBM. So the company that would become IBM was formed in 1896. You know, think about that in context of history and where things have grown and where things have changed and where we've put things, right? Big significance there. This one's just a little sort of fun thing, right? Like we have the instance of the first computer bug. The first computer bug was discovered by Grace M. Hopper. Admiral Hopper, working for the United States Navy. The first computer bug was an actual bug. It was a moth. And what's interesting about it is that we can actually see that, and I'll pull that picture up here in just a second. But it was a moth, and it got trapped in the relays of a relay calculator on a naval ship. Right? And, you know, you got to remember that at this time, you know, we're not looking, you know, no such thing as an integrated circuit yet. You know, no such thing as silicon chips yet. You know, everything is still highly mechanical or electromechanical. Things need to make connections. Things need to have, you know, parts that work together. And if something interrupts these parts from being able to communicate with one another, then it's going to stop working. Even something like a moth. So here it is. This is a picture of the very first computer bug. You can see it there taped to the logs. These are the logs on the ship. You can see the different computing processes and different things that they were doing there. And you can see that in relay number 70 on panel F, there was a moth in the relay, and they've taped it there. That's the first actual case of a bug being found. Which is pretty incredible. You know, it's interesting to see all of this history, because we can kind of think about this in a way that you know, we're able to see it. Like it's from a time period when everything was recorded, but it's still from a time period that seemed like, you know, far away, right? Because like if we look here, we can see here 1947 is when this computer bug was found. You know, that was still the time when like regular electronic digital computers were as big as entire rooms, right? Like this is in the UNIVAC-ENIAC era. So something that would be on a ship would be mechanical. So we'd still have a mechanical computer in use here. And so we get a moth flying in and getting stuck in a relay, preventing different things from making contact. And that's causing a problem. And that's the first case of a computer bug. And we can actually see, like, we can decipher these notes here and see exactly when this happened. Right? Because we see it's September the 9th, so it's almost the anniversary of it. right? We're 2 days right now before the anniversary of the first computer bug. So maybe, you know, on Thursday you can go celebrate the anniversary of the computer bug. But on 9/9 at 15:45, so that's going to be, you know, 3:45 p.m., right? 3:45 p.m. on September the 9th, 1947 is when they extracted this moth from the relay and put it in the logbook. Which is pretty cool, you know, pretty significant. We got all this information. Admiral Hopper here would become a very influential figure outside of this instance. Like, it's not just a little fun fact that we talk about Admiral Hopper here. Admiral Hopper contributed way more than just this to the field of computer science. So she might be one of the individuals that you'd be interested in learning more about. And so that's why she's one of the individuals that are, you know, an option for your module lab. But there is that. So the next big innovation came through high-level programming, right? We're still doing a lot of low-level programming, a lot of punch cards, a lot of plug boards. You know, everything was kind of broken down to machine language and encoding characters and bits and bigger programs in that sort of way. But when we got to higher level programming, that's when the game really changed for the next time. So the first high level programming language was Fortran, and it was developed in 1945 by John Backus. And I've got a question here for you, and it is, what makes a programming language high level? If you're here with me in the chat and you think you want to throw that answer out to me, please do. You know, let me know what you think makes a programming language high level. If you're watching the recording here and you want to just kind of sit and think about it for just a second, you might want to pause the video, or you might want to just kind of sit and think. I'll give you a second to kind of think about what makes a programming language high level. Because we got a peek there at what something that is low level is. Right? That machine language. That binary where we're encoding bits in an octet. That's a low level. So we got to guess here that a high level program could be the ability to execute programs. And that is kind of part of it, yeah. It's a good guess. But really what sets apart our high-level programming languages from our low-level programming languages is essentially the language itself. Right? Like we saw those bits. 0, 1, 1, 0, 0, 0, 0, 1. I can't remember that. I definitely can't write that every time I want to represent a letter A. So thanks to John Backus and people like him, we got high-level programming languages that took this language and made it more like English. Now, to the point that was made kind of in the chat live here, the ability to execute programs, that's also kind of true as well. Right? Because we need something in the middle to be our translator. So what makes a programming language high level is that it's more user-friendly, right? It's closer to English. So we kind of say that the closer it is to a natural spoken language, the more high level a language is. The further away it gets from that machine language. But that does mean we need the ability to execute it. We need the ability to have an interpreter there who can take this high-level program that was written in a language that's like English and convert it into those bits and bytes. Convert it into that low-level machine language that our computer understands. So while technically something being high level means that it's more like English, it also kind of as a byproduct means that we do have to have the ability to execute the program in a different way. Like we have to have an interpreter for that program so that our computer understands it. Which is pretty interesting. Now on my next slide here, I have an example of a hello world. And a hello world is kind of the first thing that you write when you're learning how to code in a programming language. It's essentially, you're saying, hello world, now I can do this, right? So what I have here on my next slide is a hello world in Fortran. So this is a hello world in Fortran. This would have been what a simple program would have looked like in Fortran in 1954. Now, one of the interesting things that you'll see, because Fortran is a really basic language, a really simple language, it's missing some of the functionality that we appreciate in more modern programming languages. So we'll actually see programming languages get more complex and then get easier again. And in just a few slides here, I'll show you some more examples of some hello worlds. Just a really basic programming, a program in a basic programming language. So you can see that. But just kind of keep this in your memory. Remember this. We have this program hello where we're starting the program. We're printing hello world, and then we're ending the program. But before we look at some more hello worlds, let's just talk about the first computer game for a minute. The first computer game was called Space War, and it was created by Steve Russell in 1961. And it was actually a two-player game. And we think about two-player games kind of, with two controllers or over the internet nowadays. But this was two players on one keyboard. So like one player would control WASD, one player would control the arrow keys, for example. And so you had spaceships that could fire missiles at one another. In terms of what we know today, an incredibly simple game. But I like these last 2 points, and these last 2 points are incredibly salient for when it comes to like what we'll be talking about in a couple modules. This idea of thinking like a programmer. It took roughly 200 hours for Steve Russell to program this game. That's a lot of time. Right? Like if we think about that as like a full 40-hour work week, that's 5 whole weeks. That's 5 whole weeks of working 40 hours a week to complete that game. That's a long time. Right? Like if you worked 5 weeks at your job making, whatever it is you make, $10, $15, whatever it is, like let's just say $10 for a nice easy number to work with there. Even at a regular job, working 40 hours a week for $10 an hour, that's $400 a week times 5. Right? That's $2,000 that you would expect to make off of that. Bare minimum. Right? And nowadays, when we kind of think about that to what games are today, where games make millions and millions of dollars, the very first game didn't make a dime. And I like this individual's quote here, and it really applies to a lot of the other stuff that we look at when we're looking at the history of programming. If I hadn't done it, someone would have done it equally exciting, if not better, in the next 6 months. I just happened to get there first. Wow. That's kind of a heavy statement when you really think of it. Like, it sounds on the surface like it's something that's really simple. This kind of idea that's duh. But when we kind of look at it in the scope of history, what we're looking at are people that got there first. What we learn about are the people that got there first. Not necessarily the people that had the idea, but the people that executed the idea first. Without Babbage, somebody else might have made something like the difference engine or the analytical engine. Without Holleranth, we might have got somebody else with the plugboard computer. Right? I mean, even if you think about, like, since it's North Carolina and we like to talk about the Wright brothers around here, like, there were other people at the time that were building planes and trying to fly. It was just the Wright brothers that were successful and got it out there. Right, so this is something that we see a lot. And especially if we put this into context with one of the things that people like to say, that there's nothing new under the sun. Everybody's working on similar ideas concurrently. It's just the one that actually does it that gets the credit. The one that succeeds first. Which is really something to think about as you're kind of thinking about writing code and building things and making whatever, right? So let's look at some of those other major programming languages. And look at those hello worlds. Some of these are high level, some of these are lower level. Like we have C here, which is technically a lower level programming language. But C built off of it, and we got C++, and we got C#, and we've got, Objective-C, which isn't really used anymore because Swift took that over. Well, this gives us a good idea and kind of an evolutionary idea of what programming languages look like. Because first we have BASIC here. BASIC's still in some use to this day, believe it or not. And it was an acronym for Beginner's All-Purpose Symbolic Instruction Code, developed by John G. Kemeny and Thomas E. Kurtz in 1964. So this was essentially the next big kind of programming language after Fortran. We had Fortran, we had COBOL around the same time, and then BASIC. And BASIC, the idea here is that it's for beginners. It's something that, you could do in your home. And a lot of people did, right? Like when we're looking at like the Tandys and the Commodore 64s and the Apple IIs from the from the late 70s and early 80s. Like these computers didn't come with a whole lot of software. And there was a time before physical media where you couldn't get software on a floppy disk or a CD or whatever. You got a notebook with the code in it and you had to type it all in. And a lot of that was done in BASIC. And so if we look at a hello world in BASIC, we can see that it's really, really simple. Print hello world and then end. Now, BASIC isn't used much anymore. Like we still see some like legacy systems that might have a little bit of BASIC programming in them. But by and large, this has gone the way of the dinosaurs. This isn't really used anymore. The next big innovation in programming was C. And C was probably the biggest programming innovation ever. Right? Because so many other languages came off of C. Like C++, C#, Objective-C, which again, not really used because we have Swift now. But even Java was to some degree built off of C. And so C was developed by Dennis Ritchie between 1969 and 1973. And it was used to implement the Unix operating system. So one of the very first operating systems was built in this language. And this is what the hello world looked like there. And we can see it getting a little more complicated. And if I remember correctly, this might not be regular C. This might be C++. But But one of the things to note here is that at this point we didn't have good string handling. Right? Like this says hello world in a printout. So we're able to display the string that's inside the quotations, but the language doesn't really handle strings outside of that very well. So you can see that this is actually in an integer function. And we have to return a 0 at the end to make this integer function valid. So it's almost like a little hack. Right? Because the string handling at this point isn't strong. Right? So you see we have this int here. That's for integer. And we have to return a 0. We have to return some sort of integer. Return some sort of whole number for this to be valid. And we have to do all that just to write hello world. That's inconvenient. So that's why we came up with other languages like Java. Java was originally developed by James Gosling, Mike Sheridan, and Patrick Naughton in 1991. Right? Like a lot of people think about Java like it's always just existed. But it was only developed in 1991 and released publicly in 1995. So Java is a relatively young programming language. But it is very widely used. In fact, that's one of the reasons why we chose the languages that we use here at Cleveland Community College to teach you programming. We focus primarily on 3 programming languages. That's Java, Python, and JavaScript. And these are our 3 focuses, and we include a smattering of other stuff here and there. But these are our 3 big focuses because these are the 3 most widely used programming languages in the world. Now, one of the things to not get confused is Java and JavaScript. When you start writing them, you'll see they're very similar. But they're actually not the same thing. JavaScript was actually only named JavaScript for marketing reasons, right? Because it came out around the same time, 95, 96. They released JavaScript to go along with, web development that was happening at the time. And it was actually called LiveScript at that time. But the company that was in charge of putting it out said, well, Java's super popular. And it's kind of similar, so let's call it JavaScript so more people will like it and want to use it. Right, so Java and JavaScript aren't the same. So a lot of people like to conflate them, but, just kind of keep that in the back of your head. We'll talk about that a little bit more later as well. But again, Java was derived in part from C, but it was modified to be more secure. And this is what a hello world looks like in Java. Right, we see a couple things here. Like one, we see a class here, which is the first time we've seen a class. Java is really one of the first times we get object-oriented programming to become a thing. So in order to have an object, we have to have a class. And we also see a main method here, which these are all things that you'll hear more about when we get into the Java class, which is, if you're in the programming and web development degree, you'll take that in your final semester, the last semester before you graduate, which is second year spring. And then we can see our print line here for system.out.println hello world. You can see we don't have to return any numbers. We don't have to do anything like that because Java can handle our strings simply. And finally, we have Python, which will be the language that we use a lot in this course. And we can see that Python was developed by Guido van Rossum in 1991. So we see Python and Java being developed kind of side by side there, which is also something that a lot of people don't think about. They think about Python being a much newer language than a lot of the other ones, but it's not, right? And the big thing here, and the big reason why we use this particular language, is that it emphasizes code readability and syntax, so that new programmers can express concepts in fewer lines of code. So like, remember stuff like this and how complicated that looks. And, we saw really complicated code. Code kind of got more complicated over time, but now we're making it easy again. And so in a few weeks, we'll actually be programming in Python ourselves. And we'll actually we'll write some Python and have some fun with it. And really, only one of these lines is required to do a hello world. That first line there is something that we call a shebang, which we'll talk more about that when we get to our Python module. So really, only that second line, that print hello world, is all we need to write a hello world in Python. So we went from really complex to really simple, and really simple to complex, back to simple again. And so let's finish this up, and I believe I was a little more long-winded than I intended to be about the history of programming, so it looks like we'll just talk about the history of programming for today. But we'll end up talking about machine learning. And machine learning, we kind of look at that as the next generation of programming. And I've got a little question mark there because we really don't know. Like, when we're talking about machine learning, we're talking about computers having the ability to learn without explicitly being programmed. Right? You have to have a base program, which we call a model. And then as the computer is presented more problems, it can either realize that it fits the model and accommodate it, or that it doesn't fit the model and kind of throw it out. So what we're essentially looking at here is computers basically programming themselves. And I mentioned Alan Turing earlier. And it was really Alan Turing back in the 1950s. Before we even had higher level programming languages, really, that ideated this concept of machine learning, that ideated this idea of artificial intelligence. And really, like, if you go back and you look at the history of Alan Turing and you look at all the things that he contributed to the field of computer science in the short amount of time that he had to contribute it, it's really, really incredible. One of the lines that I've said before is that if I could make a Mount Rushmore of computer science individuals, I might consider putting Alan Turing on it 4 times. Like, his contributions were especially significant, and they're things that are still being built today. Right, like the things that he was conceptualizing back in the 1950s, we're making happen right now. And in part, that's these things like machine learning, artificial intelligence, and neural networks. Now, machine learning does raise some ethical questions. So we talk about the concept of algorithm bias here. Right, because when I'm training my computer to make decisions, which is essentially what machine learning is, either consciously or unconsciously, I can also give my computer the biases that I have. Right? So it might see something and accommodate it into a specific model when it really shouldn't fit that model, but it's something that I didn't consider because of a particular bias or a particular misunderstanding or a lack of knowledge. right? And there was actually a little news story about that was incredibly recent. I won't go into it, but you could try to look it up if you wanted to. Can't remember where it was. It might have been at Facebook. But there was a problem with a machine learning classification algorithm that was classifying certain things as something it should not have classified them as. And it's those kind of things that we see when we're talking about the idea of algorithm bias and these ethical questions. Like another ethical question that's really common for machine learning is the idea of self-driving cars, right? Because that self-driving car has to be able to kind of see what's in front of it and make decisions about, based on what in front of it, how it fits its model. And it's got to make decisions when it's going to prioritize the driver or the whoever's in the car versus whatever's outside of the car. So these are things that it has to think of. Now, this is all built off of something called a neural network, which neural networks learn and they progressively improve performance on tasks by considering examples, generally without specific programming, right? Like we have this generic model and then our computer accommodates things based on that model. So like, for example, if I show my computer a picture of a dog, it can tell me if it's a dog or not. And one of the interesting things here, and one of the kind of the things that we are building, is we're trying to make computers learn in the same ways that we do, or that a human would. And so that kind of leaves me with my final thought for you all today, and it's something that you can kind of think about as you're reading and working in the module this week. I know it says discussion here, but that's more of a live class thing. Where are the boundaries? Should there be boundaries? When we're considering the limits at what we can program a computer to do, or potentially what a computer could program itself to do, where are the limits? Is it, are we considering a Terminator type scenario where, we have machines that kind of learn too well, if you will, and do all that kind of stuff? Or is it more of a Mean Girls thing where the limit does not exist? And we should be able to push this as far as we can. Where's the limit? Where's the boundary? Is there one? That's kind of what I want to leave you with as food for thought for this week. So that's it. If you have any questions, if you're watching this recorded or you think of questions later on, email me, send me a Teams message, whatever you need to do. I'm going to hang out in the chat for just a couple more minutes, just in case anybody here with me live has any questions that they want to put in the chat. We can talk about them in the chat. But that's all that I have for you today. Thank you for watching, and we'll see you next Monday, back on our regular schedule.